Thank you, Sue, very much for the invitation here to Edinburgh. And also thank you to the Charitable Cook Trust, who funded the participation of some of our US colleagues and myself included here. So thank you so much for getting us to Edinburgh. Yes. So I'm here to connect the macro and the microclimates through ventilation design, share some of my recent work. And because of the discussions over the last day, I wanted to share a little bit of my background also. Sue knows this book. She's mentioned it multiple times to many people here. Designing Spaces for Natural Ventilation, An Architect's Guide is now 7 years old. And I took about 10 years before that to write and do the research for the book. And as still sort of visible and perceived, this conference seems to be a very necessary guidebook because designing spaces for natural ventilation is essential from the start. You can't add natural ventilation later. And as we've heard also, it's so important for the physics of air movement is the consideration of three major. Thank you. Ooh, I by mistake took a pre-recorded slide into this but it didn't show at all when I was putting the slides together. Well, you can see we've worked a lot hybrid or online through our teaching in the last 2 years. Some of our slides have still sounds to them. So what I was going to say is that natural ventilation is not just opening windows. I think we've heard that before. And I always use with my students this little cartoon from the New Yorker that there are three major strategies necessary to really design for natural ventilation is the boundary conditions, to understand what's happening on the in and on the outlet. We design the flow path from the inlet to the outlet, and there is no air movement without creating the pressure differential. So no AC, but who needs it when you have this kind of cross ventilation, right? So that led from the book, which sort of is guided by the layers of the natures of flow from the landscape through the urban context, through the building, courtyards, or specifically as an important climate device, the free flow open space, and then in the English language is really good. It's the wind eye, right? The eye for the wind. And I have to put my timer back on here. And so what was missing, or where the book could only really touch upon, was the natural ventilation in the urban context, a very complex situation. And we used some of the urban morphometries from researchers, climatology researchers like Grimman and Oakey, to actually show what that means, which cities are related to which numerical canyon ratio. But there were many questions still left. And so starting with the Iowa climate and some work we did on the building scale, and we saw the Arctic vortex map earlier. The Midwest is one of the most extreme climates on the Northern Hemisphere. We have here our study area in Iowa, in the middle of the Midwest. It's a small neighborhood in the capital called Des Moines. And if you can see here, we have temperatures between maximum in the summer 101 Fahrenheit, which is pretty much body temperature, 38, 39 degrees Celsius, and it goes down all the way to minus 15. And that is pretty similar to minus 15 or even lower Celsius. So that's an extreme range. And we are also, because of the Gulf of Mexico, and between the Gulf of Mexico and the Hudson Bay, we have a lot of humidity in the summer, which is exacerbated by growing corn all over the state, because the corn takes the humidity out of the ground and spits it in the air. So another challenge in this part of the world is against common consideration or assumptions, there are still a lot of neighborhoods in the Midwestern cities which have a fairly low penetration of air conditioning. And so here you see a map of Des Moines, which has, in the center specifically, you have up to 50% of homes only with active central air conditioning. Some might have some window units, but they're fairly little effective. So that's a big challenge, and as some other researchers have noted, those are low-income, vulnerable population, often in the history of the so-called redlining in the US, which prevented maintenance and upgrades of these buildings. So one of the topics I'm going to address here is the impact of trees and vegetation. And I had the very stupid question once to my urban ecology colleague, Jen Thompson: why is there no energy model for a tree? Well, it's complicated, right? And so for this neighborhood, which is called Capital East, we actually have a very detailed tree inventory, which give us the opportunity to have detailed information about all the trees in that neighborhood. And back to the redlining issue, where the buildings are more dense, we have a higher heat island effect in those neighborhoods. So there are many issues coming together, and as a team, we are funded currently by the US National Science Foundation. We developed a modeling framework which brings people together. So, the people aspect, how people interact with the buildings, and the environmental aspect, all those issues which are more complicated and which are not yet integrated in the energy consumption considerations or in the comfort considerations of buildings. And so on the micro level, we verified a lot of the assumptions we have made, and also a lot of missing information we validated through the building we built in 2009-10 with the support of the United States Department of Energy Solar Decathlon project. This is a solar house built by students, and it is based on the Midwestern Porch concept. Here you see I used as an example my own house, with a porch which is screened in the summer and glassed in the winter. And so in this climate where you have 100 Fahrenheit, 38 degrees in the summer, high humidity, and minus 10, 20, 30 Celsius sometimes in winter, you need, and you still want to design with passive strategies in mind for the times when it's possible, you need to adapt the building footprint to the climatic conditions of the seasons. So we have cold winters where you try to reduce the envelope and you have a sun space, which is actually very effective because when it's very cold, it's actually also very sunny. And I was confronted with the situation that, I was told there are only 2 seasons in Iowa, heating and cooling. No, we proved that there is also a very nice interim season, which is probably even, similar to Europe, 6 months long, where you can naturally ventilate a building even in Iowa. And in the hot summer, when it's really hot and humid, you condition the building. Nighttime ventilation works very well when you have efficient thermal mass in the building. So we use the building based on a different NSF funded project in order to calibrate computational fluid dynamic simulation models, as you can see here. We used that study, some people might remember, also to validate that humidity actually can be integrated in the thermal comfort model, the adaptive one. These were measured studies in the house with occupants. And we do use a lot of sensors to actually validate the airflow models, which we are using here. You can see that the measured and the modeled data. So based on that work, we moved into the larger scale And here is an urban heat island study from remote sensing from my colleague, Dr. Yu Zhu, and this is the neighborhood model, which is integrating all the inventory of the trees. And we are using here a sort of, not every tree has this separate evapotranspiration value, but there are many different intricacies when it comes to evapotranspiration, which is not only shading the ground, shading the facade, but also reducing the temperature in the air. And so this project started with a presentation we showed in Dubai 3 years ago with just one tree and octomesh CFD simulations around the tree, and you can literally start moving the tree. It can grow around the buildings. And then now, based on a probabilistic model of tree building differences, we are going to evaluate how the microclimate within a neighborhood is reducing the air temperature around the buildings. A second study you can see down here, which is published also with the International Building Physics conferences last year, 2021, get the years mixed up here, to assess how green vegetation reduces the heat flux on building surfaces. This is our little test trailer here. And that work then will be fed into the urban energy model. And there's also a component which will connect this work with urban agriculture. And so the work is currently at a stage where we have the automatic meshing tool in place. In the neighborhood, you see here, this is part of that neighborhood, you see the penetration of trees. There are more trees in other, I mean, it's a fairly wooded area, but there's still a lot of blank surfaces. And so you see here the current situation, the trees are sparse. Still, there are some buildings which are completely exposed to the sun and to the heat. And the student here, Bo-Shun Gao, his PhD, defended last year. The paper is currently under review. He used that part of the neighborhood and his newly validated CFD meshing tool with the low eddy simulation. And he did 4 configurations here. He took some trees away. He took the real trees situation, no trees, and he added trees. And so these are his numbers, just to get a sense how the different cases increase the number of trees around the building. And he placed some trees in front of the building, windward or leeward, which also becomes quite important. 5 minutes, yeah, that's it. There are only a few slides left to show the outcome here. You see here one simulation where the case is no trees, right? And then you see the real trees. I can go back. You can see the flow. And so there is more, there are more trees on this side, and here you can also see that there is less velocity, but also cooler surfaces where the trees are positioned. And, whoops, now it's not moving anywhere. That one, okay, yeah. So here it's more important to look at the sectional distribution here, because that actually shows that the height of the trees has an important impact on the windward side, obviously, of the building facades. And this is nice, pretty pictures, but there's, of course, also a numerical outcome, which means that there is a number which the computational fluid dynamics community uses, heat flux and convection. It's called the Nusselt number. And you can see here that there is quite significant increase in the decrease of the convective heat transfer with the increase of the numbers of trees around the building. And it depends where the wind is coming from, and more trees are not always better, but they have to be in the direction of the wind, ideally. So the ideal outcome of this work is obviously to finally come up with an energy model for trees, or a simulated object which can be placed in front of a building or around a building, which is not only shading the building, but actually impacting the microclimate around the simulated building. And so here there's the numerical results. Buildings with trees upstream benefit more than just placing them anywhere. And so the work continues, and I just show the last few slides here with the probabilistic database we are currently creating. Those of you who might have done some CFD, computational fluid dynamics, it's very time consuming. It's very computational intensive. So you can't just do this always for each case, but we are going to provide a database for all the different variables. And the input looks kind of like this from the GIS map. The distance and the height of trees and wall R values, the heat transfer coefficients. And then combine that with a little script which gives us also percentage of shade and leaf on and off period, which means when they have no leaves and when they have leaves. And back to micro. Combine that also in times of COVID with a project here. We have our polls again. We are measuring again in schools at the moment. And hopefully by the end of the next year, we'll have a tool which can combine the microclimate with the indoor air distribution, and school operation officers or personnel can use that to assess their energy needs for upgrading school buildings for COVID ventilation requirements. So with that, I have all the reference here. If folks are interested, I can give you also those slides. And I thank you very much. We thank the U.S. National Science Foundation for funding this work, the Iowa State University's Interdisciplinary Research Program for Data-Driven Science, where I'm, as the architect, just the one who asked the stupid questions. Thank you so much.
And we're very fortunate to have the answers emerging to those questions.